All right, so today we are going to learn about the idea of velocity, all right? And specifically, we're going to deal mostly with constant velocity, but if your velocity is changing, you'll learn if that means you're speeding up or slowing down, or later we'll learn even turning. Way ahead of myself here. So we're going to deal largely with constant velocity and a little bit with what's called average velocity, all right? So here we go. All right, so probably the easiest thing to do is just dive in and do an example, all right? So in this example, we've got Roy. You're gonna hear a lot about Roy this year. He's a recurring character in the problems that you'll be doing this year, all right? And so the first thing he does is he runs 90 yards up the football field, and then he turns around and he comes back 30 yards, okay? And the problem tells us that this takes a total of 15 seconds, all right? So what I like to do, something that makes solving challenging problems a little bit easier, is we make a drawing of the path that the object follows, all right? Now, we're on day one here. These aren't gonna be crazy challenging, but as the problems get harder, this is a really, really useful strategy. So here we go. So let's see. So we've got Roy. Let's make a little smiley face. There's Roy. Oh my gosh, that's the worst smiley face ever. Let's try that again. Here's Roy, all right? And so he's gonna go 90 yards up the field, and then from there, he turns around and he comes 30 yards back. All right, so what are some things we could figure out? Well, so the first thing, new definition here, is what's called distance, all right? The symbol for distance is a lowercase letter d, and it measures exactly what you'd think that it does. It measures the total length of the path that our object, Roy, follows. So what distance did he go? Well, what distance did he go? Let's see, he went 90 yards upfield, and then he went 30 yards down the field for a grand total of 120 yards. There you go. All right, that's the distance he traveled. All right, now in physics, more often than not, we don't care so much about the distance the object traveled. We care about what's called the displacement. All right, and the symbol for displacement is the Greek letter delta, as in change in. All right, if you don't know, it's just a triangle. All right, x. All right. So the textbook definition of displacement is change in position. All right, we'll learn more about that at the very end of the video. But for now, symbol for displacement is triangle x, delta x, all right? What this does is it measures the length and the direction of the straight line from an object's initial location to its final location, okay? So my distance measured this. It measured how far he actually traveled. So that was my distance. My displacement measures the length and direction of the straight line from his initial position. So here's his initial position. Here's his final position, right? After he came the 30 yards back down the field, he ended up with this little red dot. So my displacement is the length and direction of this dotted line. All right, so let's find the length of it first. And hopefully you've got it already, right? You went 90 yards that way, then came back and went 30 yards that way. Hopefully I'm pointing in the right direction here on the screen. I never know if the camera flips around. But anyway, he went 90 yards one way, came back 30 yards. He's gonna end up 60 yards from his starting point, right? So mathematically, it's this. We're gonna go, all right, well, he went 90 yards up the field, and then, watch what I'm gonna do. I'm gonna make the 30 yards negative because he's undoing his progress up the field and he's coming down the hill, okay? Or down the field, sorry. So I'm gonna call it negative 30 yards for a total of 60 yards. And the positive one, and the positive was up the field, so I'm gonna write 60 yards upfield. All right, I don't know if upfield is a word, but you know, it's just implying this way, not that way, right? Okay, so here we've got the length, 60 yards, and the direction, up the field, as opposed to down the field. All right, so there we go. So there is our displacement, all right? All right, so, let's see, what do we got next? All right, so let's talk a little bit about calculations, all right? So in algebra, we learned that distance is speed times time, right? For us, algebraically, if you rearrange this and solve for s, we get speed is distance over time, but technically it's average speed. So see this little AVG there? That's our shorthand notation for average, all right? And so the definition of average speed, S average, is it's a measure of the average distance that an object travels per unit time, all right? So in that last example, we know that the distance that Roy traveled was 120 yards and that it took him 15 seconds. And so we can find our average speed by doing distance divided by time. He went 120 yards. in 15 seconds. Divide that and you get 8 yards per second. Now, does that literally mean that he ran 8 yards every second? Absolutely not. 120 yards is a pretty long run, and I think 15 seconds is a pretty good time. I don't know, I'm not a sports guy, but regardless, he's probably tired, and so maybe at the end of the trip he slows down, or he certainly has to stop, all right, because he goes 90 yards this way and then turns around and comes back. So he's going to speed up and slow down as he goes, right? So this is his average speed. He averaged 8 yards per second. Some seconds he went 10 yards, some seconds he went 3 yards, right? But he averaged 8 yards per second. That's what our average speed tells us, all right? Now, in physics, we usually care about average velocity. And so average velocity is probably exactly what you would guess that it is. All right, well, so definition-wise, it's a measure of the average displacement per unit time. And notice that because displacement has direction, so does average velocity. So let's find his average velocity. Well, his displacement we had decided was 60 yards up the field. And the time this took him was 15 seconds, right? Like you saw him and bang, go, he started running. 15 seconds you looked back and he was 60 yards from his starting point, right? Because he started here and ended here, okay? So let's find his average velocity. So V average is displacement over time. He went 60 yards upfield in 15 seconds. That means he went 4 yards per second up the field on average, all right? So some seconds he went, 8 yards up the field. Some seconds he went 8 yards down the field, right? But he averaged 8 yards upfield, all right? And if it would help, let's go back to this and let's take a look. I'm going to switch to the highlighter here. So think about what's happening. Ready, set, go. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5. He's going upfield. He stops and takes a break. 7, 8, 9, 10 seconds, 11, 12, 13, 14, 15 seconds, right? So as he traveled, sometimes he was going up the field, sometimes he's going down the field. He may have sped up, he may have slowed down, but on average, he averaged 4 yards up the field every second. Okay, so there we go. All right, let's talk, before we go on and talk about, I want to talk more about this idea of direction. Before we do, let's really quickly talk units, all right? I've used here units and seconds, but there's nothing magic. Sorry, I said that wrong. So far I've used yards and seconds, but there's nothing magic about that, all right? So check it out. Distance is a measure of how far you went. Displacement is the length of a line, right? These are linear quantities. You're measuring how far, right? So what we will usually use to measure distance and or displacement are meters, which we abbreviate with a lowercase letter m. But there's nothing magic about that. You could certainly use yards or feet or miles or kilometers or light years or furlongs or whatever, right? All right. And then for time, in this example, we've used seconds, which we usually abbreviate with an S. Sometimes I'll write out SEC, just in case my S looks like a 5. All right, but again, there's nothing magic about seconds. You could certainly use hours or minutes or days or whatever. So then when you find your average velocity or your average speed, or any kind of speed or any kind of velocity, it's always going to be in one of these green units per one of these purple units, right? So you could have, meters per second or yards per day or light years per minute or whatever, right? Okay? So anytime you see that word per at this point in the year, that's a pretty good sign that it's going to be your speed or velocity. And for us, usually we care about the velocity. All right, so let's talk more about direction. All right, so in physics, we often care about the size, what we call the magnitude of a quantity, and the direction. All right, so here's the deal. Up until this point, most of the numbers, the quantities that you've dealt with in your life have been what are called scalars, okay? A scalar is a number that measures only magnitude or quantity. You're just counting, right? So what are some examples of scalar? Well, the distance that you travel, right? Oh, it's 300 miles to Chicago. What's your speed? 60 miles per hour, right? So these are scalars. Just how many miles did you go per hour? Mass. this thing is made up of 40 kilograms, right? You're counting little 1 kilogram things, right? Little packets of molecules with mass. So mass is a scalar. Time, how many hours long was that movie, right? You're just counting. Energy, we measure this in joules, or if you row, in ergs. But these are all scalars. You're just counting how much of the thing went by, right? How much pizza did you eat last night? 2 slices. That's a scalar, okay? Now, a lot of the numbers in physics are what are called vectors. And vectors are these numbers that include the direction, like displacement and speed, okay? Usually, to indicate that it's a vector, you draw a little arrow over the symbol for it, all right? So a minute ago, I said that the symbol for velocity was a v. Technically, I should put a little arrow over it to indicate that it's a vector, okay? I tend to be really sloppy about drawing in those vector hats. Some physics teachers are really, really, really strict about it, and to be fair, I probably should be. But I digress. That's not a thing people say. So, some examples of vectors. Displacement is a vector. There's my vector hat. Velocity is a vector. Force, when you push a thing, you care how hard you push it, but you also care what direction you push it in, right? So force actually turns out to be a vector. I'll put a little vector hat over it just to emphasize it. Acceleration, you can speed up or slow down in a certain direction. Momentum, we'll learn about momentum later. That is also a vector. Weirdly, the symbol for momentum is a lowercase letter p. All right? Now, so how do we indicate that direction? My calculator does not have an upfield button, right? So I can't type in 4 yards per second upfield because my calculator doesn't know what to do with that. So what we do is this. So for now, we're going to be dealing with what's called linear motion. If our motion is linear, what do we mean by linear? So linear motion is motion that takes place on a fixed linear path. And I shouldn't have even said linear. Our motion is linear if it takes place on a fixed path with only 2 possible directions. Okay? When you drive on a road, you can go this way or that way, 2 directions. Okay? When you throw a ball up into the air, the ball can go up, the ball can come down, assuming you're throwing it straight up into the air. Okay? Car driving on the street, you can go forwards down the street or backwards down the street. Same thing for a roller coaster. You can go forwards on the roller coaster or backwards. A kid on a swing, you can swing forwards or backwards. A weird pulley system. Maybe you've got a box tied to a rope that goes around a pulley, and then there's another box hanging there, right? So the system can either go this way, because gravity pulls this down, or maybe Roy is over here pulling this way, right? So the system can either go forwards and down or backwards and up, 2 possible directions. All right, so when this happens, if there are only 2 possible directions that your object can go, then we keep track of the direction with positives and negatives. We pick one of those 2 directions to be positive, and the other one is negative. I will usually use math conventions, right? Think about graphing in a math class. Positive x-axis, negative x-axis. Positive y-axis, negative y-axis. So if I throw a ball up into the air, I'm going to make up positive, down negative. If I'm driving down a road, I'm going to make forwards positive, backwards negative. Same thing on my roller coaster or on my swing. All right? In this pulley example, you can go either way. You can make down, forwards and down positive, or you can make backwards and up positive, whatever. I usually go positive, negative, but not always. So anyway, once you decide which way is positive and which way is negative, you have to stick with it. And that's the deal for the rest of your problem, all right? Anytime you have an arrow pointing in your positive direction, it's positive. Any arrow pointing in a negative direction is always negative, all right? So let's apply this to a problem. All right, so in this example, it says, suppose Roy drives his scooter, so there's 2 parts to the strip. We'll keep track of the first part in purple. Roy drives his scooter east at 5 miles per minute for 6 minutes. So let's write down what we know. So here's the first part. Okay, so 5 miles per minute. Miles per minute. Oh, remember we said per indicates velocity. Miles per minute. Oh yeah, that's the velocity. All right. It doesn't seem to indicate that he's speeding up or slowing down at all. So if he's always going 5 miles per minute, then he's going to average 5 miles per minute, right? At this point, usually our velocity will be constant. So this assumption that I just made here is good. All right, and it tells us that he does this for 6 minutes, but it doesn't tell us how far he went. So I'm just going to make a note. Displacement equals something, okay? Then there's another part to the trip. It says then he turns around and he goes west at 3 miles per minute for 15 miles. Ooh, I didn't take into account the direction. So let's think about this. The trip is east and west, right? East is this way, west is that way. I'm going to make east positive, west negative. So that means that this velocity here is positive 6 miles per minute because he was going east, right? Now, in the second part of the trip, he's going west. So it tells us he goes 15 miles west. Oh, I need to make that negative. And he does that at 3 miles per minute. Again, he's going west, so it's negative 3 miles per minute, but it doesn't tell me how long it takes. Okay, so that's my given information there, written in purple and green. All right, and what we're trying to do is we're trying to find his average velocity. Well, average velocity is displacement over time. So I need to find the displacement for the whole trip and the time for the whole trip. Please hear me say this. You cannot make up your own equations. A lot of times I'll have students just take an average of the two velocities. What's the average of 5 and 3? 4, right? 5 plus 3 divided by 2 is 4. Okay? Or if you keep track of your negatives, it's 5 plus negative 3 divided by 2, which gives you 1 mile per minute. Okay? Neither of these are correct answers because he does not spend the same amount of time driving at the two rates. And so this throws off the average. All right? You have to use the equations I give you. Okay? All right, here we go. So we need to figure out the displacement. Well, let's see. So for the first part of the trip, let's see. So for the first part of the trip, I need to figure out how far he went. Well, distance equals rate times time, right? Okay, that's our average velocity equation rearranged. So he was going 5 miles per minute for 6 minutes. That's going to be 30 miles. Okay? For the second part of the trip, I need to find the time. Well, if I algebra this, divide both sides by v average, and I get that time is displacement over average velocity. So he went negative 15 miles at a rate of negative 3 miles per minute. Divide, that's going to give me 5 minutes. So that's how long the second part of the trip took. Okay? So now I know everything there is to know about the two parts of the trip, so now we can solve this thing. So let's find his average speed. Whoops. Or average velocity, I'm sorry. V average would be, well, let's see, it's displacement for the whole trip over time for the whole trip. What's the displacement for the whole trip? Well, he went 30 miles west, and then he went 30 miles east, and then 15 miles west. And the whole thing took him 6 minutes for the first part, plus 5 minutes for the second part. So I'm looking at 15 miles in 11 minutes. So 15 divided by 11 gives you 1.36 miles per minute. What direction? Well, my answer came out to be positive 15. Positive means east, so here's my final answer. 1.36 miles per minute east. All right? So, one quick last thing. At the beginning of the video, I commented that the symbol for displacement is triangle X, and I told you that the X stands for position. Here's what that means. So if an object is moving, that means its location is changing. We often need a way to describe the location of a thing. And to do that, we talk about position. So what we do is we imagine our little world and we put a number line on it. And somewhere in our little world there is an origin, right? And then we measure everything from that origin, okay? And because we're dealing with one-dimensional motion, that means there's only two possible directions you can go from your origin. So I can either go forwards from my origin or backwards from my origin, right? Sometimes the number line runs up and down if you're throwing a ball up into the air or whatever, right? So position is where you're at. So, maybe Roy is standing right here. Hello. Then I would go, the position of Roy is 6 kilometers. Okay? Now, displacement is how much the position changes. So here's my displacement, change in position. And hopefully you learned in chemistry that anytime you're finding a change in a thing, it is always final minus initial. So to find my displacement, it's final position minus initial position. okay? Notice, displacement doesn't depend on the path you followed. All we care about is the starting point and the ending point, okay? So, let's do an example. All right, so here, Roy's gonna go for a walk. So he's gonna go from a position of -7 to a position of 9. How far did he walk? Well, displacement is final position minus initial position. His ending position was 9 kilometers. His starting position was -7 kilometers. Minus negative becomes plus, I get 16 kilometers, which makes sense, right? Because he went from -7 to 0, so that's 7 kilometers. And then he went another 9 kilometers that way. 7 plus 9 is 16, okay? So then from there, it says he goes from a position of 9 back to a position of 3. So now the displacement is, I'm going to be quick here, final position minus initial position. Oops. So much for being quick. Minus so his final position was 3. His initial position was 9. So subtract and we get -6 kilometers. Notice it gives me the sign and tells me he moved in what we've been calling a negative direction because he went backwards, right? So how do we find the displacement for the whole trip? Well, option 1 is you can add the two individual ones. 16 plus -6 gives you 10 kilometers. Or you can just go, displacement is final position minus initial position, which is going to be 3 minus initial position. Notice, doesn't care about the starting, the path, just where did I start, where did it end? All right, and that still gives you the same 10 kilometers. All right, now, what distance did he run? So the distance that he ran would be the exact same thing, but without the negatives, right? So we went 16 kilometers that way, another 6 kilometers gets you 22 kilometers, all right? And notice, if we knew the time that this took, we could absolutely find the average speed and average velocity, just like we did over here for Roy here and here. There you go, one video down, 1 billion to go.